today we're going to come back to quadratics, and specifically we're going to look at some of the applications. So we've seen this example before. I've shown it to you before. I bring it up because it's just a nice example of a sort of a real life model. Obviously, when people snowboard, they don't think about these things, but perhaps an analyst would want to define how their jump was after the fact. Perhaps there are restrictions by a competition body, like you must be at least this many feet in the air after this far along. In fact, they do have such restrictions for tennis matches. Like there's like a specific constraint for being a legal serve, but we'll come back to that. So, you know, maybe we're interested in this, maybe we're not, but either way, we have this model that is quadratic. And the quadratic means that the pathway can be modeled with a parabola that has an x squared in it, in its function. And we've learned that parabolas could come in the form of like this, you know, with some ABC. That's called standard form. They could also come in a form that's kind of factored out with vertex HK, and this is vertex form. And so you should be able to move between these two pretty easily. And so if we think about how you would go from vertex form to standard form, what do we do? Like how would you, if you had something in vertex form and you wanted it in standard form, what would you need to do? Get something like this, right? We could talk about the vertex, we could talk about potentially where the maximum is, where the minimum is. But if I want to get it into this standard form, I'm going to have to like multiply this out and collect like terms. You're going to have a question like this where they say go from vertex to standard or from standard to vertex, right? So from vertex to standard, you're basically expanding. Standard form helps us with being able to factor. And we might want something to be factored if we're concerned with where is it equals 0, right? Because remember, we were able to solve quadratics for 0 by factoring and then finding their x-intercepts. And vertex form offers us this like maximum point, right? That vertex point, which is also very interesting sometimes. And obviously the other letters in vertex form will help you determine the shape, if it's up or down, and if it's wide or narrow based on the A value, right? So I'm just recapping things that we've learned. So if you take a look at the model approximation they've offered, it's negative 16 t squared plus 22.9 t plus 9. They've like approximated this with a computer system to kind of find the function that represents the guy's jump. And so let's say we're interested in what's the highest point he got to, how far, how high did he get to in the air? We would want to find that vertex, right? Okay, so let's just recap. So we can go vertex to standard. That would help us find like where he lands, for instance. But if we want the highest point, we're interested in the vertex then, right? And so the vertex, that would be the other way. So we'd be going from standard, because this is in standard form, right? It doesn't really easily tell us much about where the vertex is. The only thing I can see right here is that it's downwards facing, because if it starts with a negative for my highest power, the t squared, that means I'm going to have a negative on my A, and that means I'm going to have a downwards facing parabola. That's the only thing I can tell from this format. I could try to factor it. Obviously, it looks quite hard to factor, so it's really, you know, there's going to be decimals. I'd have to use the quadratic formula to factor and find the zeros. But this question is interested in where the maximum is. So that means we're interested in vertex form. So if we have standard form and we want to go to vertex form, we learned how to do that for just more basic examples. So what was sort of the general strategy when we started with standard form, let's say x squared plus, this is a different example just to jog our memory here. Like, what was something we did to put that into standard form or into vertex form? We want it to have a square, we need to complete the square, right? Nice. So, this one, I picked a super simple example because you can already have that there. And then you have your x plus, well, we'll just do this here. We want to figure out what to add and what to subtract, right? And so we took half of 10, squared it. So we want to add 25, we want to minus 25, and we want to keep that. So this part right here then completes the square. And that, like, you should really, if this is not natural for you yet, just like factoring quadratics, completing the square needs to become kind of fluent. So I'd suggest do some more practice if you haven't done enough. So that was the general sort of process. And then now we know that the vertex is negative 530 for that example. And that helps us see, okay, at negative 5, there was a maximum or a minimum of 30. In this case, it was upwards facing, so that was a minimum, right? So this would have been at negative 530. Just reminding you of all the things we've sort of done all together on one page. Now, the other thing for standard to vertex is sometimes it's not as nice as this, right? This was a very convenient example. I chose it just to illustrate a simpler example. But if we're looking at something like this, right, that gets a little more complicated to do the completing the square process. So what we did in the past is we developed a general strategy for finding the vertex without completing the square by sort of generalizing completing the square for A, B, and C, right? So using A, B, C in standard form and just finding the H component, right? And if we think of that H component, remember we had to first factor out the A, and then we took the B, which was B over A, and divided it by 2 in order to square it. So this 5 technically came from, let's see here, if this is A and B, so that X value for the vertex, it technically came from the negative of this 5, because it's always the opposite. And then we took the 10 over 2, right? Now, if you had an A here, you'd also have to multiply or divide by that A. So if you remember, the vertex always was negative B over 2A from completing the square was always the X value of a vertex. The Y value is way too complicated to find. You just, like, once you find the X value, you can plug it in and find the Y value. It's much easier that way. And so if you try that, negative B, so that'll be negative 22.9 over 2A. And then you'll find the X value for the jump. That won't be the height yet, but that'll be the time at which it gets to, or where that vertex is. And then you can plug it back in for T and use a calculator to find the height at that point in time. So that is a nice thing to do in application problems when numbers are weird and all you care about is the maximum or minimum. But if you're asked to, like, graph this specifically, it might actually help you to complete the square, because then you'll have the vertex form. But the negative B over 2A is always a nice way to double check if you've done the process correctly. So it's just like another way of, right? Like right here, I could already know that the vertex X value is going to be negative B over 2A, which is going to be negative 2 over 2 times negative 1 which is a 2 over 2, which is a 1. So right away, I know that in my vertex form, I'm going to have, in this bracket, I'm going to have an x minus 1 because it's always opposite. But I don't know what that is, and I don't know what that is, right? So this is a check, like I know that it'll be a -1 in the bracket, but perhaps I want to do the full process to figure out the rest of the pieces. Let's take a look deeper at this example. So I chose a relatively simple example because again, I want to connect the concepts that we've been working on. So one of them was, yeah, you could use the vertex formula for the x value of the vertex. And that gives you one piece of information. You know that at x equals 1, you'll have a line of symmetry and you'll have kind of some sort of parabola. But like, let's see what else you can identify. Like, don't use a graphing calculator, but just, are there any other pieces of information that just by looking at this example, hopefully you see it, it's a little small, I know, -x squared plus 2x plus 8. Are there any other pieces of information you can tell me about what the graph might look like? If we set x to 0, so what are we finding there on the graph when we set x to 0? Meaning we're finding f of 0. So what are we actually finding then? Easy to find. So we know that the y-intercept is 0, 8. So we know 0, 8 is 1 point for sure. Nice. Okay, what else do we know? So if we did y-intercept, could we do x-intercepts? How do we find x-intercepts? So think of reversing what we did here. If we set x equals 0, yeah, so you would want f of x to be 0 or y to be 0, right? So for x-intercept, you let y be 0. So in this case, we'd be interested in this question. And how do we solve something like that? We had several ways. So what's one way? Factoring. Yep. Right. Remember, so we had factoring. This one's probably pretty easy to factor. We had the quadratic formula. We had completing the square, which gave us the quadratic formula. Those are basically our two ways, or three ways. So if we factor it, let's try and factor it. Let's get that negative out so it's easier to look at. X minus 4, x plus 2, does everyone agree with that? So what does that tell us about the graph? What other points do we know now? So 4, 0, and -2, 0, right? So at 1, 2, 3, so this is 1, 2, 6, 7. Didn't quite count that right, did I? Let's just pretend that we have 4, 0 here, and -2, 0 here. So because the 0, 8 is not quite in the center, I'm assuming that my max will be somewhere here. Like I'm starting to see that because of the 3 points that I have. And also because I know it starts with a negative, so I know it's downwards facing. That's another thing you could have said. It's downwards facing. And also that implies it has a maximum. So, okay, we have our x-intercepts. Now, this is really important because we're going to be looking at x-intercepts, but we're not going to call them x-intercepts. We're going to call them zeros. So on Alex, if you see something asking you to find the zeros, they are asking you to find x-intercepts and vice versa. Okay, so our zeros means where it crosses the 0 line, right? Those are the zeros. They're also sometimes called roots, probably because back in the day, they were only concerned with quadratics, and the opposite of a square is a root. But obviously, roots exist for cubics and powers of 4 and powers, anytime it equals 0 is a root in general. You'll probably just see zeros and x-intercepts. Okay, so we have some information here, and there's one more, there are a few more things we can say. And some of those have to do with looking more at the vertex form and not just the standard form. So far, standard form helped us get to here, right? But what happens when we start looking at changing the form? Sorry, it's shifting around there. These are just extra practice examples. Okay, so how can we take this? We'll start again here. F of x equals negative x squared plus 2x plus 8. How can we figure out the vertex form? We know what some parts of the vertex form, but we haven't done the A part and the K part, right? So why don't we do that, completing the square process? Because we don't ever want anything at the beginning there, you're gonna have to pull it out, just like you would any A value. And you can choose whether to keep that 8 inside that bracket or just kick it out right away. I'm just gonna move it to the side here right away because I don't really, it's just hanging out, right? So now I have this x squared minus 2x, and now I have to decide what I'm adding and subtracting to complete the square. So what number do we need to add there and subtract? Nice, because half of 2, and then it's always, we're always adding, whoops, plus 1, but then minus 1. But that minus 1, I don't want it there, right? Because I only care about this part. Anyone remember what we do there? This is affecting this in order for it to leave. It has to be multiplied out by that. So now I have that, but that -1 came out as -1 times -1. So now I have this x minus 1 squared and plus 9. So that tells me a little bit more. So what is the complete vertex now that I see that? 1, 9 from h and k in there. Okay, so your vertex is 1, 9, which does make sense with our picture so far, right? And so what we can say, and we know it's downwards facing, and we also know it has not had any sort of stretches or compressions in any of the directions, because there's no number in the A component and there's no number in front of the X. So there's no sort of changing the basic shape of the parabola. So it'll just go like 1, 1, and then 2 over will be 4 down, right? And it'll just have your classic parabola shape. So now we know more about it. There's a couple other things you could get asked. You could get asked for domain. You could get asked for range. So, you know, domain is always all real numbers for parabola like this. And the range always depends on that vertex. So some of your questions will just say a range and they'll give it to you like this, which means you're gonna have to find the vertex first and determine if it's upwards facing or downwards facing in order to find the range, right? So in this case, we can look at the range, everything from -infinity up to 9 because of the vertex. I'm trying to show you like all the different things you could get asked, because each of these things would be a separate question, but really they all pertain to the same graph. So having an interconnected knowledge of how these things are different or the same is really, really important. And the ways that you could cross-check your work, right? So like we said, this part told us that this should be 1. So I see that here. I could have also put f of 1 to check what happens at 1. And if I plugged it in, I should get 9. Because obviously if I plugged in a 1 here, I'd get 0 plus 9 is 9. But if I plug it in here, -1 squared plus 1 times 2 plus 8. So -1 plus 2 is 1 plus 8 is 9. So either way, like I'm cross-checking now, I'm saying, does it all work together, right? The other thing that I want to highlight here is there is a tendency I notice in just when you do your work, these two processes, one of factoring and one of completing the square, are sometimes swapped. What I mean by that is not that it's intentional, but because you've learned both these things and you've practiced them so much, you don't want to just rest on the fact that, oh, I just do whatever is more comfortable. You have to understand which one does what, right? Like choosing which one. If I want to figure out where the zeros are, I'm going to want to factor. If I want to figure out where the maximum or range is or the vertex is, then I need to get it into completing the square, right? So they answer two different questions, and just understanding that those are two processes you learned, and they just have a different result depending on what you do. Okay, so that's the like overall overview of all quadratic stuff. One of the questions, just to kind of give you, I think the hardest one other than the word questions is going to be when they show you a graph and they're going to give you 2 points on the parabola. And I'll explain this in the, if you ask for the explanation, but these points might be random in the parabola. So one thing you can play with, and I won't do this now, but if you get stuck, bring it back next class and we can try it. Just consider what the standard form is. Like say you want that form. They kind of give you the vertex and then they have 2 points. So if the vertex was 2, 3, you already know to plug in 2 and 3. So really the only thing you don't know is the A. And so what that does is then you could plug into, maybe this was 0, 5, and honestly, I don't know if that's going to work because I just made it up. But you could plug a 0 and a 5 in here, and you could make sure that the A works with that. That's it. So understanding how to use the formulas to your advantage. It's just like when you were doing line equations, you're plugging everything in and seeing what's missing. That's the strategy there. The other type of question that you're going to get, and you have on your written assignment, is this. The questions that apply, basically all of this, have to do with questions where either you're looking for a maximum, or you're looking for a minimum, or you're looking for the zeros. And so I'm going to show you a few different sort of classic problems. Let's say you have 1,200 feet of fencing, and we're not going to do this shape, but we're going to do, we're trying to fence in an area so that there's 2 regions, not 3. Okay. So because of these are all parallel and like lined up, this is obviously just like a 3D kind of model of it. So you have a fence. So essentially you have what? 1, 2, 3 of those that are the same, right? And 2 of those that are the same. So that means we have 2 variables because we have the purple and the blue, right? So as soon as you see that, you could call them L and W for length and width, or you can call them X, Y. Let's say these are X and these are Y. So all of these together, so there's 3 X's and 2 Y's, should equal 1,200. But if you imagine these X's and Y's being different distances, like I could have drawn the same shape like this, right? So what's the problem there if it's a farmer and he has animals that want to go in there? Like that's kind of problematic, isn't it? You're like cows or whatever are going to be all lined up and squished, whereas like maybe they can graze or chickens or whatever he's putting in there, right? So there are better ways to do this sort of arrangement and worse ways, and they have to do with, for a farmer, what's important is area. He would want to maximize the area. So even though the same amount of fencing exists, you want to create the biggest area. And so if we want to create the biggest area, we need to consider what the area equation is. And we have to base it on one variable, either X or Y, either L or W. Let's say I'm making it based on X just so we have X's, but you could do it the other way. So what that means is I need the length and the width, right? Because area is length times width. Because if I want X to be the variable, that means I have to solve for Y. I'm just going to solve for Y here. Move the 3x over, divide by 2. So y is negative 3/2 x plus 600. And so this is going to be my area formula. And what I want to do is I want to maximize the area. So let's just take a look at this. If we go a of x and we simplify that, multiply in, so that's negative 3/2 x squared plus 600x. So already we see that it is a quadratic because it had two sort of sides, and which should make sense because when you get area, you usually get centimeters squared or feet squared, right? It's a square unit. So yeah, let's just kind of look at that. Right now it's in standard form, right? Because it's kind of like we're seeing it like this, plus 0, A, B, C. It's in standard form. You could do several things with this. You could ask the question, when is it maxed? You could also ask the question, when is the area going to be 0, right? And obviously, if you had it in factored form, which was right here, you'd see, well, if x was 0 or if y was basically 0, that's when the area would be 0. So that's not an interesting question, but the max area is an interesting question. And so we can do a few things. We could graph this on Desmos just to get an intuition. We could use our knowledge from previous things like, okay, it's downwards facing. Maybe I can figure out what the x value of the vertex is. That'll tell me what x value maximizes the area. Because it's downwards facing, it has a maximum. So if it's downwards facing, I know there is a maximum. If this was not a negative, then I would know that there is no possible way to have a max area, but there's maybe a possible way to have a minimum area, right? So what's that vertex? Maybe just take a moment and see if you can figure out, based on the vertex formula, you know that the x value is going to be negative b over 2a. Can you find what that vertex x value is going to be? And then if you've done that, figure out what the y value would be. Yeah. Okay, cool. So let's see how that pans out. Negative b over 2 times a. Oh, and that fraction actually ends up working out quite nicely because the 2's cancel, and 600 over 3 is 200 with the 2 negatives canceling. So 200 would be my x value maximum. And then to find the other value, you're going to then have to go back to one of the formulas that you had that relate the two. It depends what we're being asked. So if we want to say the side lengths, then I'm going to have to come back to this for side lengths. If I'm interested in what the max area is, I'm going to have to actually go into either do this, Or if I find the x and y, then I can just multiply them together to get the area, right? So many ways of getting there once you have that 200. So let's just see. 3x plus 2y is 1200. So if vertex of maximum is a 200 for x, then you'll have to do all this. That's the 600 minus that, so 2y is 600 because you've subtracted it. So that's where you get 300. So the vertex, you have to be careful here. The vertex itself is not 200 comma 300. The length and width are 200 and 300, right? So we need 200 on 3 sides, feet, and 300 on 2 sides. And then now the area is obviously going to be 200 times 300, which is your 60,000 square feet. So when we graph our sort of A of x, we're going to get at 200 for x, we'll have the 60,000 here. And it'll be something like that. And I think these will actually be our 200 and 300 because our area of x. Like, I'm just saying, like, you can go back to the different things. Like, your curiosity is pushing you forward. So let's just graph that initial function here that we had for A of x. So the scale has to be really pared down because see that 60,000 is right there. Okay, so my prediction wasn't quite accurate in terms of the zeros, but what we got was 0 and 400 were the zeros of this function, while 260,000 was the vertex of this function. Hopefully you're starting to see the connections here, the zeros, and then the vertex maximum minimum, right? Once you have the ability to create this sort of function that you're trying to maximize, that's where you can use your vertex formula for your x value. And then when you input it back again, in this case, you'd get 60,000 as your output. And every context is going to be different. There's like maximizing the volume of a box. And on the other slides, and on these slides, I'll include these again, you have a whole bunch of examples here with different situations and answers. So you can try those out for practice if you'd like. We'll just take a look at a couple here. This one is a little different because in the other questions, it's more area based and maximizing the area. In this one, it's a little more like businessy in the sense that you have been given information about a few things. One is that they tell you that they're packaging, this is super relevant right now, they're flying packages across to lots of people, which is kind of like Amazon, I guess. So the cost for this company to send or deliver X parcels per flight. So X is number of parcels per flight, and the cost. So maybe it's like a base cost of this much to fly, and then plus 7 per parcel to deliver, something like that. So that is the cost of X parcels to get sent. Okay, that's it. That's all we know so far. Okay, let's keep reading. The price per parcel, so the amount that they charge their customers per parcel is going to be 22 minus 0.01x. So let's say charge for, so this is how much they pay to do that. And this is how much they make, right? So what is the revenue function? So revenue per parcel. And revenue means how much money are they bringing in? Okay, so what would we do there? Profit is what you make. So the profit that you make is how much you bring in minus the cost of doing that you have, the cost to you as the seller. Okay, so first we need the revenue in order to find the profit function. Because they're interested in, obviously, because it's capitalism, they're interested in maximizing profit. But revenue, so if each parcel, they charge this much money for each parcel, say they have 20 parcels, they're going to have to charge 22 minus 0.01 times 20 per parcel. So if they only send 20 parcels in total, if that's all their volume, they're going to have to charge this much per parcel. So that's what helps us figure out how much they're charging per parcel. So if you have this much per parcel, you'd have to go times 20 to get the total amount of dollars that you're going to bring in, right? If you had 50 orders, you're going to have to multiply that by 50. If you had 30 orders, you'd have to multiply it by 30. Does that make sense? I guess like the more volume you have, the less you can charge per parcel. That's why it's minus 0.01. So you could see it as, well, you're going to do X parcels times the 22 minus 0.01x. That's going to be how much money you're bringing in, because you're charging this much dollars per parcel. And this is the number of parcels you have. So you get in, I'm going to write it as a quadratic. You get in that much money, but you're going to now have to subtract this away because that's your cost for sending them. So that's how much revenue you have. So that's how much money you get in. And now you're going to subtract away the money that had as a cost to you as the seller. And so once you have that, now you can consider all of everything that is going on in your company based on one variable, the volume of parcels that you are having as an order. So 22 minus 7x is going to be what, your 15x, and then your minus 2025. And again, it's a quadratic because you have two kind of variables going on. You have the number of parcels, but then you have the price that kind of depends on how much volume you have. So that gives you that square. So if we graph that, we will see that it is a negative shape. So that means it is downwards facing, which means there is a maximum. And because this is profit function, that's good for your business to know that you will have a maximum profit based on getting a certain volume. And so the input is getting a certain volume of parcels being ordered, and that'll maximize your profit. You can imagine that if you were maxed out to the limit, it would start costing you way too much to deliver those orders. Like there's a breaking point in business. Like you're trying to hit that greatest potential. So how could we figure out that maximum? So if, let's say I don't want to, too lazy to put it on a graph, what's another way to figure out what that maximum is? Yeah, good call. Get the vertex. That's what a maximum is, really, is we're interested in the vertex. So we could figure out that x value by going negative b over 2a. So, and again, this is your x value. So think about what your graph is. X is the number of parcels ordered, right? So when you find your negative b over 2a, you're not done. You still have to interpret that based on the context. You might want to plug it back in to your function in order to find actual maximum profit, right? Because x is just the number of parcels that helps you get there. So what's your negative b over 2a? Negative 15 over 2 times that. So again, you just have to use a calculator. So what would that be? 15 over 0.02 is 750. So that means you need, at 750 parcels of orders, you get a maximum profit. And then obviously you could use this function to determine what that profit is, either earlier or probably easier just right here.